We're now interested in figuring out how the aileron deflection and rolling rate affect our lifting line solution. So here I have the general equation for our lifting line algorithm. This is our method for solving for these capital A sub n Fourier coefficients in our infinite series solution, and they depend on the twist in the wing. Okay, alpha is our geometric twist, and alpha L0 is our aerodynamic twist. And so it turns out that an aileron deflection and rolling rate, they change our alpha minus alpha L0 at any theta location. And so in general, we can write alpha at any z location minus alpha L0 at any z location is equal to what we had before, which was alpha minus alpha L0 at the root minus omega, capital Omega times little omega of z. So that was our washout distribution. Plus, we're now going to say some delta A is our magnitude times some distribution chi of z for our ailerons minus p times z over v infinity. And so this is, these last two terms now, this is our aileron term and our rolling rate term. These are basically how these two affect the alpha minus alpha L0 at any location. So if we have some aileron deflection, then that can change our zero lift angle of attack, for example. And we're going to multiply that by some distribution of that change and a magnitude, just like we had a distribution of twist and a magnitude of twist or washout for this term. And then finally, this term on the right is our rolling rate, and that's just a linear, it's directly proportional to z. So our change in angle of attack there is directly proportional to z because it's linear. You know, the further out on the wing you are, the larger change in angle of attack you'll have due to rolling rate. Okay, so let's look at this term here, this chi of z, and see if we can write an equation for chi of z. And we're going to do that by looking at this aileron distribution on a wing. And I'm going to draw this with positive z in that direction, and we're going to look at chi. And the way we're going to remember that positive z in the aerodynamic coordinate system actually goes out the left. So this is the left wing, and this is the right wing. Okay, just in the coordinate system that we're using. And on this wing, so let's draw this wing up here. We've got some aileron, and we're going to assume for our analysis that it's perfectly symmetrical, so that the left aileron is located in the same span-wise location as the right aileron, and that they have equal and opposite deflections. Okay, so we're going to call this ZR, that's Z root, and Z tip is that tip location. Okay, so and actually these would be negative because our Z axis goes out the left wing. So this would be positive Z root and Z tip, and those would be negative Z root and Z tip on the right wing. Okay, so let's put these on this plot down here. So so on our left wing, we've got Z root and Z tip, and on our right wing, I put those aways out there, that's okay. We've got Z root negative and negative Z tip. Okay, so that should be symmetric. It's not quite, but you get the picture. Okay, so let's look at what chi of z now looks like. This is going to be equal to, so if we have a z location that is less than minus zt, then it's going to be 0. We didn't change the twist in the wing at all in the region where we don't have an aileron. So chi of z is going to be 0 for z is less than minus zt, so that's in this region right here. Okay, then we get into the actual aileron region, and And the amount that our alpha minus alpha L0 or zero left angle of attack is change depends not only on the deflection, but also something called the flap effectiveness, which we've talked about before. And so that flap effectiveness can change along the aileron. So it would come up, and that flap effectiveness could be a function of z if we wanted it to across that aileron. So we're going to say that flap effectiveness, which is a function of z, that's what it's going to be from minus zt to minus zr. Then from zr up to, or negative zr to positive zr, again, we have zero effect. So 0 from minus zr up to positive zr. And then on the left wing, we have the opposite effect. So it will come down here on the left-hand side and be some function of z. So that would be negative flap effectiveness as a function of z from zr up to zt. And then for z greater than zt, we're at 0 again. So that's this region here. Okay, so that's what this chi is, simply a distribution of effectiveness of flap effectiveness, section flap effectiveness as a function of z, which is 0 when we're not over an aileron, and when we're over an aileron, then it can be a function of z. And then we're going to multiply that by delta A to get the actual change in zero lift angle of attack, or alpha minus alpha L0 on the left-hand side. Okay, so with this, we can now, and the fact that this is just a linear term out here, we can actually write this alpha minus alpha L0 in terms of theta instead, just by doing a change of variables. And so what we'll get is this equation here up here. Our general equation will be capital A sub n. I'm not going to rewrite the stuff in the brackets there, times sine n theta. So it's just this, that goes into this bracket here, is equal to, and now we want to take this equation and write it in terms of theta instead, which is, we just do a change of variables. So it's alpha minus alpha L0 at the root. That's just a constant, minus omega, capital Omega, times little omega of theta instead of z, plus delta A times chi of theta, plus, and now this linear term here, once we do the change of variables, we can actually write that as a p bar. That's a non-dimensional rolling rate times cosine of theta, and p bar is defined as the rolling rate times our span over 2v infinity. This is just a general definition of, or method for non-dimensionaling our rolling rate, just a conventional method. Okay, so we can put that in terms of what we're going to call a non-dimensional rolling rate, p bar. Okay, and so now we have our fundamental equation here. We need to solve for these capital A sub n's, but we can see that we can actually divide them up like we did before to look at planform effects from this first term. We can look at washout effects from this term here. We can look at aileron effects from that term there, and p-bar effects here. And what we do is write a different summation for each of these effects, where we use then a decomposed Fourier coefficient here. So we're going to say that capital AN, we're going to define it as little an times alpha minus alpha L0 at the root, and then minus b sub n times capital Omega plus c sub n times delta A plus d sub n times p bar. And all we're doing again is dividing this up into 4 different summation terms. And so instead of solving for capital AN, we're going to solve for these little an, bn, cn, and dn from 4 summation equations. which all have the exact same form. So the first one is going to be the summation of little an, with that stuff in brackets, times the sine of n theta is equal to 1. Then we're going to have a summation for b sub n, that same stuff, equal to little omega of theta. We're going to have a summation of for c sub n, to solve for c sub n, same equation there. And on the right hand side we've got chi of theta. And finally, summation d sub n is equal to cosine of theta. Okay, so this is how we come up with our decomposed Fourier coefficients. We solve these system of equations, and the internals of each of these are identical. It's just the right hand side that's changing for each of these. We're going to store them in an, bn, cn, and dn, and then we can reconstruct capital AN by adding them all together and multiplying by these magnitudes. So BN will be multiplied by the amount of washout, Cn by the aileron deflection, and Dn by our non-dimensional rolling rate. Okay, and so that then gives us the capital AN terms that can be used in our general solution for gamma, or our distribution of vorticity as a function of theta. Remember, that's equal to 2b v infinity times the summation n equals 1 up to n of my capital AN Fourier coefficients times sine of n theta. Okay, and then once we have that, we can also get the lift distribution, which is equal to rho v infinity times gamma. So that gives us our lift distribution as a function of theta or z. So that gives us a lift distribution on the wing, and that now includes the effects of any aileron deflection. It includes the effects of the aileron design, where those start and stop. Also their effectiveness, this section flap effectiveness, epsilon f. It also includes any effects of rolling rate, and like before, it also includes planform and washout effects.